Here's our second sample problem for the topic on capacitance. The problem says find the total capacitance of the network shown or circuit shown, and this network is in parallel connection. Okay, the next one is we are asked to determine the charge on each plate. What is the charge here, what is the charge here, and what is the charge over here, and then finally find the total charge. So actually this problem is straightforward because we can solve for the total capacitance, since all the capacitance or individual capacitance they are already given. So we just apply the equation or formulas for this and we can solve that. And for this letter B, to determine the charge on each plate, so we have this C, we also have the voltage, because since this is in parallel connection, then that means if this is 48 volts, then that means this is also 48, this is also 48, and this is also 48. So Q is equal to C times V. We have C and V, so we can solve for Q. So once we've solved for Q, Q1, Q2, and Q3, then finally we can solve for the total charge. Okay, so let's do this. Okay, so number one is solve for total capacitance. So recall that the total capacitance for capacitors in parallel connections is simply equal to the sum of the individual capacitance, so C1 plus C2 plus C3. Okay, and then let's substitute the values. This is 860 and 1200. 800 plus 60 plus 1200. So let's do that. 800 plus 60 plus 1200, and that's 2060 or 2060. 2060, and the units are, or the units is in micro, because this is microfarads. So microfarads. Okay, next one is let's solve for the charge on each plate. Okay, so charge, or maybe we'll do it here instead. So solve for total charge on each plate. Okay, so recall Q is equal to CV, so therefore we just simply substitute. So Q1 is equal to C1 times the voltage given. Q2 is C2 times the voltage given, or across that capacitor, and then Q3 is equal to C3 times the voltage. Okay, so let's substitute the values. C1, this is 800. So 800 microfarads times the voltage is 48 volts. Okay, Q2 is 60 microfarads times 48 volts, and C3 is 1200 microfarads times 48 volts. Okay, so let's do the computation. We have 800 times 48, that's 38, since this is in micro, so times 10 to the negative 6 times, how do we do that, times shift 10 to the negative 6, so this is 0.0384. So 0.0384, because this must be converted to, so recall, converted to must be converted to farads, and the units of this must be in coulombs, so C, or coulombs. Okay, next one, Q2 is is 60, and let's multiply this already times 10 to the negative 6, and then times 48. This is 0.00288. So 0.00288 C, or coulombs. Then for Q3, this is 1,200 times 48 equals, and this is 0.0576 coulombs. Okay, and therefore for number 3, or step 3, so we can now solve for total Q. So Q total is just simply Q1 plus Q2 plus Q3. So this is 0.056 plus 0.00288 plus 0.0334. I think 384. And this is 0.098. So 0.09 0.0988 or 988. Right, so that's the answer. Okay, so next one is, let's do another problem. Okay, for the next problem, this is still we still have to input the values. So it says here, find the voltage across and charge on each capacitor for the network shown. Okay, so the voltage is 120 volts, and the capacitance here, let's say C1, that's 3 microfarads. Right here, this is C2. Let's say this is 4 microfarads, and C3, 2 microfarads. Okay, so we have a combined series and parallel connections here. So the C2 and C3, they are in parallel, and the combination of this, or the equivalent capacitance of this, is in series to this C1. Okay, so let's do the solution. Okay, so first step is, if we analyze this, C1, C2, and C3, they are all given, so we can solve for the total capacitance or equivalent capacitance, and then work our way back to solve for the charge, or for the individual find the voltage across and charge on each capacitor. Okay, so for the individual voltages and charge. Okay, so solve for number 1, solve for equivalent capacitance. Okay, so the figure will be something like this. So C equivalent, or CE1, let's just write CE1, and this is C1, and this is still 120 volts. Okay, so we are going to solve for CE1. So CE1, since it's in parallel connection, the CE1, so that's just 4 plus 2. So C2 plus C3 is 4 plus 2, and that is equal to 6 microfarads. Okay, so therefore CT is equal to, Okay, so therefore, this is right. Therefore, CT um, would be so 1 all over CT is equal to 1 all over the value of C1, that is 3 microfarads, plus 1 all over 6 microfarads. So if we do that, okay, so 1 all over 3, okay, plus 1 all over 6 equals, okay, and then 1 divided by the answer, that is equal to 2. So therefore CT is equal to 2 microfarads. So that's the total capacitance of the circuit. Okay, next step is, okay, the total charge is recall that the equation is Q is equal to CV, so CV. So if we are solving for total charge, then this should be total capacitance, and the voltage should be the total voltage. Okay, so CT is 2 microfarads, and then the voltage is 120 volts. So 2 times 10 to the negative 6 microfarads times 120 volts. Okay, so 2 times this is 2.4 times 10 to the negative 4, or if in terms of micro, then that's gonna be 1 2. So we move this decimal point to the right, and that's gonna be 240. Right, so 240 times 10 to the negative 6 micro coulombs. Okay, so next is let's draw this. So from figure 1, let's say here's our figure 1. So from figure 1, so Q would be, let's copy this. So our Q, we have a charge of Q, which is just equal to Q1, which is equal just to Q over here. So the total Q, let me write it here, Q, let's just write QT is just equal to Q1. Okay, so what else? If we have this Q1, we have this C, then we can solve for the voltage drop of this capacitor. For CE1, in order to solve for the charge in C2, and C3, we need to solve for the voltage. We must solve first the voltage here, the voltage drop. Okay, so let's do that. Then recall that Q is equal to, so Q is equal to CV. Okay, and V is equal to Q all over C. Okay, so what is the Q? So we have 240 volts for CE1. Okay, at CE1. So Q, that is 240 microcoulombs. Q is equal to CV. Okay, let's write it here. Microcoulombs, and then the capacitance is in farads. So capacitance, this is 6 microfarads. So 6 microfarads. So 240 divided by 6, we have 40 volts. This is 40 volts. So CE1, this is the voltage at CE1. Okay, so now let's draw. Maybe we'll do this as step 3. Now let's draw. Plus, minus, we have here the capacitance, and we have C2 and we have C3. Okay, so our C3, recall that this is already given. C3 is equal to 2, and the C2 is 4. 2 microfarads, and C2 is equal to 4 microfarads. But the voltage, since we already know the voltage here, the 40 volts, then voltage 2 is equal to 40, right? And this is also 40 volts because it is in parallel connection. Okay, so therefore solve. Let's solve now for Q, Q2, and then Q3. Or let's say we can now solve for Q2 and Q3. So Q2 is just simply C2 times the voltage, and Q3 is just C3 times the voltage. Q2 is equal to C2 times the voltage, and then Q3 is equal to C3 times the voltage. Okay, so C2 is 4 times 40, and this one 2 times 40. So 4 times 40. This one is 2 times 40 volts. Okay, so if we do this 4 times 40, that's going to be 160, and let's just write microcoulombs, and this one is 80. 2 times 40, that's 80 microcoulombs. Okay, so in summary, we are asked to find for the voltage across and charge on each capacitor. So first what we did was to solve for the equivalent capacitance, and then what else? After finding that, then we can solve our way back. Solve for Q, and then we can now solve for the voltage in each capacitors. So the voltage here is just simply, okay, we haven't solved it yet, but you can still solve it. Q1 is just equal to CV. So we have the Q already. We have this Q, and then because Q2 is equal to Q1, then the voltage 1, or maybe let's write it here. So for voltage 1, for voltage at C1, so Q is equal to CV, voltage is equal to Q over C. So our total charge is 240. Sorry, this should be coulombs because we have times 10 to the 6. So this is coulombs, or 240 microcoulombs. Okay, so 240 microcoulombs times the capacitance times 3. So times 3 microfarads. This is 240 divided by 3. That's I think 80 volts. Okay, so if we check, so let's check. So voltage rise must be equal to voltage drops. So our total voltage supply is 120 volts, and we have 80 here, and here we have 40. So I think that's correct. 80 plus 40. So therefore, okay. Okay, so I think that's all for this computations.